be finishing the LFP module today, which will give us another 5 lectures to talk about EEG signals, which I'm going to start from Monday onwards. Today, after the class, I will post another assignment. This is an EEG, a MATLAB based assignment. And you get 2 weeks plus this weekend to work on it. Um, this assignment also carries 20 marks. So, in effect, the LFP module has the lion's share of the overall, number of classes as well, and marks as well. Previous assignment was also 20 marks. And then we'll have 10-mark assignment for the EEG module, which I'll give once the EEG module is over. And then there's the uh, grant proposal. Okay, so we had finished talking about time frequency analysis in the previous class. Um, and we had talked about very briefly about matching pursuit algorithm as well, which allows us to do get a very nice time frequency power spectrum shown here, and a change in power spectrum shown here. Okay, are there any questions on this part, or can I move on and discuss something else today? Today we are going to cover what is called coherence analysis, which is a very popular and important type of analysis done on brain signals. Okay, so let's get to coherence then. So let's start with a question. The question is as follows. We know that whenever we present a stimulus, there's a prominent gamma rhythm in the LFP. That's what you see here, right? So that's the gamma. Each electrode picks it up. So now I can ask a question. If I look at two electrodes, each one is picking up the gamma wave. Is there any relationship between these waves? For example, are they occurring at a particular phase with respect to each other? Secondly, I can ask whether there's a relationship between gamma waves in the LFP and spiking activity. Are spikes occurring preferably at a particular phase of the LFP, for example? Okay, so these are the questions. How do we answer those? Let's talk about the first question. How can we answer that? Any ideas? You guys can guess. Just think about this. This is a very real question, of huge practical relevance. You have got two data from two electrodes, right? LFP1 and LFP2. That's the data that's been provided to you. There are 76 trials. You get an estimate of gamma amplitude and phase in each trial. And I want to know how consistent is this phase relationship. How will I test that?
Correlation.
Correlation between what and what?
The gamma waves that are recorded from one electrode and from other electrode.
Okay, so correlation gives you another time series, right? When you correlate two functions, you get another function. What are you going to do with that? Plus, if you correlate two sinusoids, you'll get another sinusoid back. I mean, a sinusoid at the same frequency.
I was thinking of a cross correlation for like phase and all of that. You can check.
Right. So that's what I was saying. That yeah, that's what Srishti was also saying. So if I've got a sinusoid at 40 hertz, let's say, and another sinusoid, which is, let's say, a little bit phase shifted. So this is LFP1 and LFP2. When I do a cross correlation between the two, so at particular phase difference, they will be perfectly aligned and will give a large value. And as I move and become out of phase, you'll get or and then you'll be anti-correlated. So it will also be a sinusoid if you cross correlate the two. And the actual phase will depend on the phase difference here. This and well, the way I've drawn it, it's phase aligned, but yeah, there is some difference between the trough here and the trough there. It will get reflected here. So how do I measure whether this phase is consistent across trials? Whether the two LFPs are maintaining some sort of a particular phase relationship?
Um, a convolution between time frequency of both of this LFP1 and LFP2.
Convolution between time frequency. What do you mean by that?
So, like in previous part, we compute the Fourier transform and then we get the frequency time plot, or like somewhat like just like a big we get a big matrix itself, like the time window and the of the frequency, and we get another also for the LFP2, and then we can just overlap it each other and then check whether the gamma rhythm just converge between two.
Yeah, so these kind of analyses only tell you about the magnitude of gamma. They don't tell you anything about the phase. This is a power spectrum, energy spectrum. So all the analysis that we have talked about so far only deal with whether there is a gamma present in the signal or not. This is the average gamma across trials. It tells you nothing about the phase relationship between the gammas that you get in different electrodes. So this is for a single electrode, electrode 1. And if you had done another electrode, you would have got a very similar result, a gamma sitting, a gamma spectrum. So you would have got a similar plot like this. My question is that whether the phase of gamma that you have here and the phase of gamma that you see, are they consistent across with each other across trials?
I have a very
That
naive answer.
analysis you can't do by looking at the power spectrum because it has no information.
Can't you just add up all of the waveforms and like if they're not in sync, then they're going to cancel each other out because sinusoidal kind of thing.
So add what?
Adding the different LFP waveforms together,
So
if they
this
are in
with that,
phase,
are you saying this with this?
yeah.
Um, okay. Well, so there are some issues there. First, what if the magnitude of this is too large compared to this? Uh, Adding directly is not a good idea, but you are sort of in the right direction. So I'll tell you what the strategy that is often used. So let me zoom out from here and get to the Jamboard. And so suppose I am interested in the consistency in phase across two electrodes, between across trials. That's the question. So the question is that suppose in one trial I find out that LFP1 LFP2 is a little bit shifted, like so. Okay, so there is some phase lag between the peaks here. I want to know that if I look at these signals at a different, in a different trial, whether I will have a similar phase consistency, which means that in a similar another trial also, the two sinusoids will be shifted in the same way or not. That's what I want to find out. Okay, so phase consistency doesn't mean that this delta is 0. Even if I have two sinusoids that are completely out of phase, they are actually phase consistent. They are consistently out of phase. So I'm right now interested in whether the phase difference is consistent across trials or not. I want to think of a metric that tells me about this phase consistency. So here's how I can do this. This analysis is done as a function of frequency. So for each frequency, well, so first I look at the Fourier transform. I compute the FFT. So then I get here some spectrum for both of the signals, LFP1 and LFP2. Now, for each of the frequencies, let's say I'm interested in 40 hertz gamma frequency. I'm asking whether the phases of LFP1 and LFP2 are consistent with each other across trials. So for each trial, I'll get a Fourier spectrum. For each of the trials, I'll get a Fourier spectrum. So think about the 40 hertz component. For LFP1, the signal, it's a complex number. So you can think of it as some amplitude and some phase. Both of these are functions of frequency. At each frequency, it's a complex number. So I'm writing it down as amplitude and phase. So this is your spectrum for this is the FFT of LFP1, and likewise LFP2 will have similar thing. And you can think of both of them as two vectors of amplitude A1 and A2 and phase of phi1 and phi2. Okay. So the first thing I want to do is actually look at the phase difference between the two. That's the measure of this delta. So a simple way is to just take the conjugate of this. Remember, when I take a conjugate of a signal, it just puts a minus here, and then I take a product. So the product of x1 f x2 star f where this is your x1f and this is x2f, is just a1, a2, e to the power j phi1 minus phi2, all as a function of f. Okay, and this is nothing but the cross spectrum product of the spectra after doing a conjugate on the second one. Okay, so just think about this for a minute. Let me go back here. So the question, I suppose, is clear with to everyone. I'm looking whether there's a relationship between the gamma waves. So what I do is find the spectrum. So this is the Fourier transform. XKF is the Fourier transform of signal 1. YKF is the Fourier transform of the second signal. K here is the number of tapers. This is the multi-taper. If you don't want to think of multi-taper and you're doing just Fourier transform, just make capital K equal to 1. So this summation goes away. You're just left with X star F, Y F. When X is equal to Y, this is power spectrum of X, because X conjugate X is just mod of X square. So this measure coherency is defined as the cross spectrum divided by the square root of the product of the autospectra. This looks complicated this way, but it's actually very easy. It's actually almost trivial to understand. Think about what is going on here, but instead of thinking about spectra, again think about it as if each of these numbers, x star f and y f, is just amplitude multiplied by e to the power j times the phase. Okay, so here's what it is. If only a single taper is used, and I denote the two tapered Fourier transform as this, ak multiplied by e jk and bk multiplied by e theta k, then the coherence is nothing but ak multiplied by bk e to the power j phi minus theta. This is what I was showing you here. So whatever have I done? For each trial, I am generating a vector. The amplitude of this vector is A1 multiplied by A2. It's the product of the amplitudes of the individual signals. And the phase is just the difference of the respective signals. So this is the phase difference. If two signals are out of phase always, the vector will be like this. If the two signals are always in phase, which means that then the phase difference is 0, then it's going to be like that. Okay, and if it's a sine for one and cosine for that, another one, it will be like this. For each trial, I'm getting a vector. So then all I need to do, if I've got 76 trials or some n number of trials, I need to know whether for different trials, are they pointing in the same direction or are they pointing in different directions. So this is highly phase consistent. This is not consistent. If all the vectors point in the same direction, it is. If they point in different directions, it's not consistent. Very simple. So how do I now get a number that tells me how consistent it is. And this is where what Swikrut had mentioned good. I could just take the sum of all these vectors. Why so? Because if it is consistent, all the vectors point in the same direction. So there's hardly any cancellation. You get a big number. If they are all over the place, when I take a sum, I get a very small. So I just take the sum across trials. Suppose I've got trials, and I am just taking the sum of these for the kth trial and e to the power j phi 1 minus phi 2 for the kth trial. The only problem in this case is that the final answer that you are going to get is going to depend trivially on the amplitudes. If the amplitudes are very large, even after cancellation, it's going to. So how do I address that? I just need to divide it by something that accounts for this, and that is trivially done. This is the so these numbers account for the absolute amplitude. So the whole thing is a normalized measure of phase consistency, and this is what coherency is. That's all I have done here. That's all being done here. XX, when I put yk equal to so a star xk is just xk mod square, right? When I this is ak e to the power minus j phi k. When I take the product, I just get a thing gives an idea of what the phase consistency is across trials, and that's what coherency is. Coherency is a complex number because the numerator is a complex number. Coherence is just the absolute value of that, and turns out that this value always lies between -1 and 1. Sorry, the modulus will always lie between 1. Okay, so any questions on coherence? This is such a important concept that it keeps coming up in any type of neural signal analysis. Because people who think that oscillations are important because, let's say, you want to make communication channels in the brain, or you want to somehow modulate the position of a spike by putting an oscillation. They're always thinking of the phase difference between oscillations or between spiking activity and oscillations. So this keeps coming up everywhere. The concept is actually very straightforward if you think of it this way. If you think of it as vectors. Otherwise, mathematically, it looks a little bit complicated. Okay, any questions on coherency? So another concept that is often used if you don't want to deal with the amplitudes is you set all the amplitudes to 1, which means that here each of these vectors is just set to 1. You say that, okay, I'm not going to care about the fact that the amplitudes are different across trials. I'm just going to make each of these amplitudes equal to 1 and just check then whether the phase, and then just take the average of these vectors. This is called phase consistency, and it's similar to phase coherence, and it's similar to coherence phase, but it doesn't take into account the amplitudes. It's also called phase law. Okay, so let me just coherence is a complex quantity. Coherency is defined as the cross spectra divided by normalized by the product of the auto spectra. Turns out it is biased estimate of the true phase relationship because it depends on the that are used for average. Why is that? It's not very hard to understand. Suppose the signals are truly there's no relationship. So if you got 1,000,000 vectors, on average, they would just be completely out of phase, and you will end up getting a very small vector close to 0. If you had, a lot of vectors, but if you only had a few vectors, then when you take the average, you may not get a small vector just because it's not the case that every vector has its also anti-vector also present. If you had done 1,000,000 trials, yes, would have been the case. A small number of trials, the resultant sum average may not be a small vector. In fact, it turns out that the bias has a form of 1 by root of n when n is the number of trials, which means that even if the true phases are the phase coherence value is going to have a form which is like 1 by root n, where n is the number of trials. Only when the number of trials are large is this number going to be very small. Okay, so it's biased by the number of trials that are used in for averaging. We will do a question later on where we'll try to prove this, why it is has this form of 1 by n. Another thing to note is that the coherency depends on the phase consistency, which is this thing, but it also depends on amplitude correlations, which means whether A and B are somehow related to each other or not. This final value that you see here, we think that it only depends on how the vectors are aligned, but it turns out it also depends on the magnitude of these vectors. It's a concept that should be appreciated more than. In fact, we actually wrote a paper just on this and we showed that how phase consistency gets biased by amplitude correlations in a rather good way occasionally. Okay, finally, when you talk about coherence, the absolute value of phase difference is not important. What is important is the phase consistency. It means that whether I get all the vectors pointing in this direction, or whether they are pointing in that direction, or they are pointing in this direction, they will all have the same coherence, close to 1. because they are always phase consistent with each other. Here we are talking about sinusoids that are in phase. Here they are shifted by 90 degrees. Here they are out of phase. But it's okay, because they are always phase consistent. They always maintain a particular phase relationship with each other. So coherence just tells you it's which is this normalized sum of these vectors, just tells you whether the phase consistency is maintained irrespective of the absolute phase difference. Okay, any questions? That's all I'm going to talk about coherence, and then I'm going to show you our results for in our LFP data. There are any questions, please ask. Okay, looks like everyone is happy. So the reason why Cronux is so popular in neuroscience, this Cronux is the package that implements multi-taper. That it's that because it has very nice functions to compute the coherency as well. So there's this, it's the same, command structure that you use. Use a command called coherency C, and it will give you the LFP coherence. The coherence between the LFP signal, in this case during the baseline period. So if you run this command, set of commands, you get this. You'll get the green trace. And if you did the same analysis for the stimulus period, which is between 0.2 to 2.4 seconds, you would get the red trace. This 100 hertz, this peak here is just the refresh rate of the monitor, which ought to be phase consistent because the same refresh that both the monitors are catching. But note this, when the stimulus comes on, comes on, there's a gamma rhythm, and what this analysis is showing is that this gamma rhythm is actually quite phase consistent. That is why you see a peak in the gamma rhythm. This is the stimulus period. This is the baseline. This is the actual data that I have given you. LFP coherence actually, like the power spectrum, tends to have this 1 by f sort of form. Of course, it's now limited between 0 and 1, so it's not like a 100-fold decrease. But so that means lower frequencies are always more phase consistent than higher frequencies. This is true for all biological signals, even EEG. But then if you see an oscillation, often you see a peak there as well, which means that these oscillations are phase consistent across triads. Okay, so this analysis that I showed you, this is done for each frequency. For each frequency, you get a vector. So the coherency measure is also computed as a function of frequency. So as a function of frequency, now you can which frequencies are more phase consistent than others. Okay, and remember, LFP coherence is a measure across two LFPs. You can't compute the coherence of one signal. You need two signals. So here's the result. This is actually from a paper, that we published a few years ago. We show the LFP coherence as a function of inter-electrode distance. Remember, I've got a grid of electrodes. So I can ask how is the phase consistency between two electrodes that are separated by only 400 microns, which is the distance between neighboring electrodes, or something that two electrodes that are far from each other. So what I do is I look at all the neighbors, all possible neighbors, and compute the LFP-LFP coherence and take the average. So I've got 32 such electrode pairs, and I get this place. All electrode pairs that are between 0.4 and 1.2 millimeters, millimeters, 0.4 millimeters is 400 microns. There are 121 such pairs, and then the phase the LFP coherence is given by. As you go farther and farther, notice that the coherence is falling. However, it actually doesn't become zero. And you would say why it's not becoming zero? It's actually only because of the bias that I had mentioned. The true coherence actually should be zero. If I take a lot more trials, then this thing will become closer and closer to zero. But with only 76 trials, settles to some value which is non-zero. The peaks here correspond to the refresh rate of the monitor and the second harmonic of noise. In US, the noise line noise is 60 hertz. So this is second harmonic at 120 hertz. However, when you present a stimulus, you see a nice peak in the gamma range, which is maintained even when the electrodes are separated by 4 millimeters or so. Okay, and this is the peak in the alpha range. So it's pretty cool. What you are saying is that the gamma rhythms in my grid maintain a particular phase relationship across trials. Okay, and this is maintained even when the electrodes are, although the absolute value falls, which means that if your electrode pairs are farther apart from each other, like the gamma rhythms are not always consistent. In some trials they will be like that, in others they will be somewhat off phase. So this would be a vector in this direction, that would be a vector in that direction. There was going to be more cancellation as opposed to a case where they are close to each other, in which case they are always very close to each other. Okay. So this is the result from a lot of electrode pairs that we had, of which I have given you 2 electrodes for doing the analysis that you can do using these commands. Okay, any questions?
Why do we see the line noise of, sorry, I'm saying the first harmonic of line noise, but not the actual line noise? Or we are able to
Yeah,
suppress the
because
line?
our shielding is very good. Our shielding is so good that it took care of the first harmonic. And then, but it only finds the first, the fundamental, but not the second harmonic. Uh, in our data that we have collected here at IISc, we do see a peak at 50 also. In the US, in my postdoc lab, the shielding was very, very good. So, and then these, these devices are also sort of very good in killing the first harmonic. Whenever you test, you only care about that. But, these things don't get, uh, eliminated. We did not use a notch filter though. There are ways you can notch this out completely, in which case you see a dip in the power spectrum. We did not use a notch filter. So this is actually just good shielding that has taken care of it. Okay, so I'm now going to show you just data that we have published from the same data set that for which a couple of electrodes were given. So this is a published result where we showed that if you increase the contrast of the stimulus, so you're showing a grating to the monkey, but you're increasing its contrast, the center frequency of gamma increases. Now I hope you guys can appreciate what these plots are. This is a change in power spectrum from one monkey and another monkey, and you can see that this peak is shifting up. It's like a staircase. And in this power spectrum, the peak is shifting this way. If you look at LFP coherence, this is monkey 1 and monkey 2, that also shifts as it should because the gamma peak is shifting. But if you ask what's the phase difference between average phase difference, the average phase difference is close to 0. What that means is that the coherence is high, but the vectors are always pointing in the same direction, which is 0. Which means that the gamma is actually properly aligned. The phase difference is 0 for both monkeys. This kind of a plot obtained by looking at the vectors and then taking the average. So you get an average vector. The amplitude of that vector is plotted here. This is the amplitude of the coherence. And the phase, which is this theta, is plotted here. Okay, so in the homework assignment, these are called rose plots. You will be asked to generate the rose plot for the data that you have been given. Conceptually, that's what it is. That's all there is. It's just the phase difference plotted here as a histogram. So of all the electrode pairs, we are just simply asking how many times I get a value of 0, how many times I get something else, and it's almost always 0, which means you're almost always perfectly phase aligned. Okay, so I have answered the first question, which is there a relationship between gamma waves recorded from different electrodes? And the answer is yes. There are gamma waves recorded in different electrodes, and they seem to maintain a particular phase relationship. And in case of LFPs, the phase relationship is 0, which means that the phase difference is 0 on average, which means that they are phase aligned. And this bump here shows that it's more consistent in phase than neighboring non-gamma frequencies. Now you ask, what's the relationship between spikes and LFPs? All of this analysis was just LFP signals recorded from two electrodes. That's it. So let's think through this a little bit. Let's think through this a little bit. What I could do, so remember that I've got an LFP signal. So I've got an LFP signal, function of time, and I've got some spikes. Time. If it is the case that spikes are occurring at a particular phase of gamma, let's say it's always occurring at the trough of gamma. Let's say that is the case. Then suppose what I do is I take a small piece of the LFP signal around each spike, like so. And I'm going to just simply average all these pieces. So then I align them. So this is onset of spike, let's say, and the different pieces are like this. These are the different pieces of the LFP. If it is the case that they are always occurring at a particular phase of the LFP. Then when I average these, I'll get something like that. Will still be a dip there. But if they are occurring at random phases of the LFP, when I average that, I'll get a flat line. Okay, so let's see what is happening in our real signal. So these segments are called spike triggered LFP segments. So what we are going to generate is a spike triggered average of the LFP. This is the average of the LFP segments around each spike. Whenever you see a spike, you just take a segment. It could be overlapping segments. If the spikes are too close to each other, you will get two overlapping segments. That's all right. And then you just simply average all these segments. This is called, so this is a function called get STA, which is provided to you in the resources folder. So you just run these commands and you will get something like this. Is again for line. This is for stimulus. Okay, so spikes record in the stimulus period. This is in the baseline period. So notice, first of all, that during the baseline period, there's this slow wave. This is actually the alpha rhythm. Very slowish wave, very weak alpha, very low frequency stuff. So we don't pay. But when there is a stimulus, it seems to be oscillating like this. So it seems that spikes times 0 are occurring at a particular phase of the oscillation in the signal. Now, what is this ugly stuff here? This is just the low frequency component of the action potential itself. Remember, there's a spike here, so the spike will have some signature in the LFP, and that's just this. So it's going to corrupt my estimate of the phase here. I'm trying to estimate whether this oscillation is large enough compared to the, this is the averaged oscillation when you average across all these segments. So my idea then is to somehow get to an estimate of how strong this is, which will tell me how well the spikes align to the particular phase of the oscillation. So I was coherence field. Now I'm going to try to do what is called spike field coherence, spike versus field. Okay. So before I get to that though, I'm going to do something which is often done in the field. If I've got two electrodes, electrode LFP1 and spikes 1 and LFP2 and spikes 2, there are actually 4 combinations that I can do. I can compute the spike triggered LFP taking spikes from electrode 1 and LFP from electrode 1, which is what I had shown, or spikes from LFP2 and electrode 2 and LFP, but also the cross ones where I take spikes from electrode 2 and LFP from or spikes from electrode 1 and LFP from electrode 2. Why would I want to do that? The idea is that the LFP from two electrodes, as we saw earlier, is more or less the same. It has the same to 0. So I need a proxy of the LFP oscillation from this electrode and ask whether spikes are occurring on that. But this electrode also catches the extracellular action potential, which is this thing here. This is what I don't want. I'm only interested in the I really don't want to deal with this. It's very hard to get rid of this. It's present here and it's present here as well. So if I take the LFP from a neighboring electrode, the phases are more or less aligned. So it will give me some estimate of the signal, but I won't have because the spikes that so often a trick that is used in the field. It's also not a foolproof trick because there is some residual effect of spiking from a different electrode, so that complicates our analysis. But to a large extent, the spike related transient is reduced. Take the electrode from use the LFP from a electrode. So crossroads. Okay.
Was your voice breaking at my end only or for
At a
others
particular
also?
phase of the
Yeah, sir's voice is breaking.
yeah, your voice is also breaking. So is it breaking for everyone? Yeah, others hear
Yes.
me.
Yeah, we were hearing your breaking voice.
Okay, is it okay now?
Yeah.
Okay. So well, so we've run out of time. So and anyway, my voice was breaking. So I will again start from this part in the next class. Just um, uh, uh, just look at these slides one more time, and we will cover this and look at spike field coherence, and then we'll be done. So we will finish this off in the next class, and then we will go to EEG analysis. Okay. So I will give you an assignment in which you have to run basically these codes and generate phase coherence plots and so on. So it's going to be a very useful exercise for your project. Okay, so I'll stop here for today. If there are any questions, please go ahead and ask.